as Maddie said, my name is Hanna Mularcyzk. I'm a junior at Walter Payton College Prep, and I'm here today to talk about a topic that isn't discussed very often at CYT, math. And before you groan or sigh or whatever, I thought of math, I want to tell you that you're not alone. In my experience in high school, math has gotten a particularly bad rep, even at some kind of more STEM-oriented selective enrollment schools like Payton. It isn't uncommon to hear a kid beam about their history or art class, and yet it's more often you'll hear a kid complain about their math class than praise it. And I wanted to kind of get to the bottom of why this is happening. So I took a survey on 73 representative Payton students, sorry, big number. And I asked them to rank rank the 5 core classes, math, science, history, English, and world language, in terms of their favorite. And math got second to last. Kind of not a big surprise. Only 8 students said math was their favorite subject, and more than half the students ranked math 4th or 5th out of the 5 subjects. Again, this isn't a big surprise to me because math doesn't get a bad rep. I knew this. But what was more interesting in the survey is the second question I asked, which was for the students to rank their classes in terms of which they thought were most creative. And this time around, math got dead last. Only 6 students ranked math as the most creative. Thank you to those 6 students. But more than a third, or around a third, ranked it last and least creative. I mean, out of the 5 core subjects, math is ranked dead last. And then, to me, it started to click why people didn't like math so much. Because it wasn't creative. Or rather, because they thought it wasn't creative. In my opinion, math's the most creative subject. And to be fair, I've been in math camp for 2 years. I'm part of the math circles here in Chicago. I'm on the math team at school, et cetera, et cetera. But I think because of that, or maybe as a reason for that, is because I think I see the true beauty in math. And, one second. And I see math for something that isn't just formulas or algorithms or equations, but it's a creative process, unlike, as you see, a lot of other people. Because math's so much more interesting than high school classes give it credit. Sorry. So math, in my opinion, a lot of people's opinion, and the idea of math is that you're proving kind of fundamental truths about the universe, which is really, really, really interesting, because math doesn't just apply to people, or the world, or the solar system, or a particular physical system or model. The math literally applies to anything that has number, anything that has a quantity. And it's math, it's algebra, it's calculus especially, that's kind of the underlying groundwork of the universe. It's underlying science, and it's underlying almost everything we know, which a lot of people kind of don't give it credit for. And kind of these proofs that have furthered math and have furthered all these amazing things we've discovered aren't based on rigor. They aren't based on, on equations or algorithms or, or punching numbers. They're based on ingenuity and creativity. And I'd like to share one of these with you today, one of these proofs. It was first published by George Cantor in the 1890s, and today this proof's still notorious for its simplicity and elegance. Some of you may have heard of it. I'm not really sure. Probably not. It starts like this. A lot of you probably read that book by John Green, The Fault in Our Stars. There's like a really cheesy and annoying quote from it that's, some infinities are bigger than other infinities. And unfortunately, that quote's correct. We're going to dive into that today. So kind of as a preface, it's really hard to count infinities because it's like literally infinity. So the best way to do that is we're kind of going to, as a preface, we're going to use this method that I was once told by someone, not really a reliable source, but that was used by shepherds in ancient times before they had numbers and counting systems. So, pardon the picture. But when shepherds had sheep, and they wanted to let them out to graze, they couldn't count them. So they didn't really know how many sheep were coming back, how many sheep were going. So they came up with a system where every time they would open the pen for the sheep to graze, and every time a sheep left, they would move a rock into a bowl. And they would do this for every sheep until every sheep left, and the sheep would graze and do their grazing stuff. And then they would come back, and on the way in, they would remove a rock from the bowl each time a sheep came back in the pen. And when they looked at the bowl and saw it was empty, they knew that all the sheep that had left had come back. They didn't have to count them. And kind of what they did by doing this is that they created a matching between the sheep and the rocks. So they didn't have to say, oh, there are 5 sheep, we're good. They didn't have the number 5. So instead, they said, well, if we pair a sheep to a rock, and we notice that there aren't any left over in either group, we know that these sets of objects are the same size. Likewise, if you had fewer sheep than you did rocks, and you pair them up, you notice that that rock over there is left over. And you notice after you pair them up and you have a leftover object, then that group must be bigger, therefore. So we're going to do the same thing, but now with numbers. Kind of as a practice, I have 2 sets of numbers here. First, 1, 3, 5, 7, 9, and then 2, 4, 6, 8, 10. And if I asked you which set of numbers is bigger, or which set of numbers has more numbers in it, you can say that by which set is bigger or larger. You would easily say, well, they're the same size, because they each have 5 elements, they each have 5 numbers, which is pretty clear. But again, if we were going to do what the shepherds did, we could pair them up and see the same thing. So since we paired them up, and we noticed that, hey, there's not a number left in the bottom set, there's not a number left over in the top set, these sets have to be the same size. And you might be thinking, well, that's kind of a dumb thing to do, we could just count them. But you can't count infinity, which is what we're going to get into next. So looking at some slightly bigger sets, we have the natural numbers, which start at 1, the whole number starting at 1, 1, 2, 3, 4, 5, on to infinity. And then we have the integers, which are the natural numbers, but also kind of the negative counterparts. So you have negative infinity to positive infinity, all the whole numbers in there. And if I were to ask you the same question, are these sets of numbers the same size? It's a little harder. You can't just count them. And that's when we have to be like shepherds again. So if we were to match up, just maybe do a quick matching between 1 and 1, 2 and 2, 3 and 4, and so on and so forth, we're pairing them up, and we would say, well, geez, all these are paired up to the right, all these infinity numbers over here, but there's an infinite amount of integers left over on the left, which is troubling. So you might say, because of that, well, the integers have to be larger than the naturals, so there have to be more integers since they're left over when you pair them. The issue with that is that's incorrect. So the deal with this is that you have to be really careful with how you list the integers. If you kind of notice how these sets are set up here, you have your naturals. You have the naturals starting at a single number, a single value 1, and extending to infinity in one direction. The integers, however, are a problem because you're starting at 0 and you're extending infinity in 2 directions. Therefore, you can't match them up. But a way to fix this is just think about a better way to list the integers, which is this way. So naturals are listed the same way, but the integers, on the other hand, instead of going to infinity in both directions, if instead you list them as 0, 1, negative 1, 2, negative 1, 3, and so on and so forth, you're actually, that's actually all the integers, and it only goes to infinity in one direction, which means you can pair them up with the naturals. And you're not going to have any left over. So if I were to take any number in the integers, I would guarantee that it was paired with the number above it in the naturals, which would guarantee there aren't any numbers left over in either of these sets after I pair them up, which guarantees they're the same size. Pretty cool. It gets better, trust me, sorry. So these are called accountable infinity, which is one size infinity. And kind of the criteria for being in this infinity is kind of this process we did with the integers, which is that you need to be able to list the infinity, starting with, again, one value, and going on infinity in one direction. And what's special about these lists is that these lists kind of have a pattern where they're guaranteed to cover every single number. So I could find any integer in this list if I went far enough. It's guaranteed to hit it. Same with the naturals. So we want to see if we can create a list of these other numbers, and we're going to look at these other sets of numbers. The next we're going to look at are the rational numbers, which are just pretty much fractions between integers. And believe it or not, the rational numbers can also be paired up the same way. They're also the same size. Kind of confusing chart. I'm going to pick it apart. So what this chart's showing us is that we're going to start with 1 over 1 in the top left corner. And as we move to the right, the denominators are increasing of these fractions. And as we move down, the numerators are increasing of these fractions. So as you can see, if this chart were to go on forever, infinitely, kind of by the dot, dot, dots, we would eventually hit every single rational number on this chart. Every rational number is going to be covered. If you have a number divided by another number, it's going to be on here. integers divided by each other. And what this means is that we can create a list kind of through this. So kind of a really clever way we can do this is we're going to start over here at 1, 1, and we're going to zigzag our way through these numbers to create a list. And again, since this list is going to zigzag throughout this whole chart and can zigzag indefinitely, that list is guaranteed to cover every single rational number. Because it's going through this entire chart, and it'll eventually hit every rational number. We're not going to miss any. We're starting with one number. It's going to infinity in one direction. Therefore, it can be matched up with the naturals. Now again, since rational numbers can be negative, I'm doing the same negative positive flip-flop thing here. But we created this list of rationals just by going through, again, that chart, going along that diagonal little zigzag pattern. So we creatively just found a list of the rationals that, again, can be paired up with the naturals without any left over, and therefore the naturals and the rationals are still the same size as infinity. Cool. We're going to look at one more example. This is where the proof part comes in, called the real numbers, which include the natural numbers, include the integers, include the rational numbers, but also include irrational numbers, which are pretty much just decimals that go on forever, indefinitely, like pi, the square root of 2, stuff like that. And the question is, are they the same size as infinity as the naturals, the rationals, and the integers that we just showed? Can they be paired up in this way? And that's analogous to saying, can we create a list of them, starting at one value going on towards infinity? A list that'll guarantee we cover every single real number. And the answer to that is actually no. And you could say, well, okay, well that makes sense because it's probably really hard to come up with a list. You can't really zigzag through the real numbers. There's so many of them, and all have different dimensions. I mean, they all have a different number of decimals. There's a lot going on there. But this is math, and you don't know until you prove it. So this is where our good friend George Cantor comes in. And he said he's going to do what's called a proof by contradiction. So what he's going to say is that saying, okay, we're looking to prove that no list of real numbers exists. No list that covers every real number. And he says, okay, well let's assume the opposite and prove that that can't happen. It's kind of a weird way to think about it. It's called an indirect proof because you're kind of indirectly proving it. An example of a proof by contradiction, in case that was a little confusing, is if you were accused of doing a crime, and you were called to court, and you're in front of a jury, and they're trying to get you to admit, or they're trying to prove that you caused the crime. And you said to them, okay, well, assume the opposite of what I'm trying to show you. Assume I was at the crime. Then, I would have had to have been at this place at that time. However, I have proof, I have an alibi I was somewhere else. I can't be in two places at once, therefore I didn't do the crime. That's kind of what a proof by contradiction looks like. You're going to assume the opposite, and you're going to prove that that runs into some fundamental error, like being in two places at once. Okay, sorry. Okay. On to the proof. So George Cantor said, well, geez, let's assume that there is a list of the real numbers. This is a hypothetical list. Now, the actual numbers that are there actually don't matter at all. It's the idea that they are there. And we're saying that hypothetically, this list starts at a single value and it's going to hit every single real number. And then Cantor said, okay, well, let's create a diagonal on this list. So if you notice the highlighted diagonal over here, that goes through the numbers, you might think, well, that's kind of weird, but I'm going to explain it. So you're gonna take the first digit of the first number, the second digit of the second number, the third digit of the third number, and so on and so forth. And notice how the highlighted numbers, we're going to turn those into their own number at the bottom left of the screen. So kind of 13770 is going to go down there. We just created a number from these diagonal digits. And then we're going to do something even weirder, and we're going to create a number such that every digit in our new number is different than the digits in the first number. So I just did that by adding 1 to each digit in the first number. So we create a number that has each of the digits in this number is not the same digit as that number. So just the nth digit of this number is not the nth digit of that number. And by doing that, you might think, well, why the hell did we do that? That's so weird. But it's actually super duper 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 clever. I'm going to explain why. So we just created a number that isn't on the list that we just said contained every number. And I'll show you why. The first digit of our number doesn't doesn't match the first digit of the first number by how we created it, right? The second digit of the number doesn't match the second digit of the second number in the list. Therefore, it can't be that number either. Likewise, the third digit in our number doesn't match the third digit in the third number, by the way we made it. Therefore, our number can't be the third number in the list. In fact, by this reasoning, by this diagonal, our number can't be any of the numbers in this list, period. And therefore, the list we assumed had every real number is missing one. It's missing our number that we just created. In fact, it's missing a lot of numbers. And that was George Cantor's proof. And because you can't list the reals, you can't match them up against the naturals, and therefore, this is a whole other size of infinity. This is a bigger infinity, which is kind of weird to wrap your head around. That's the proof. Thanks for listening. Sorry. I have an outro. Sorry. That's like not the end of this speech. That was misleading. Okay. I think that's like a super duper duper cool proof. No, not all proofs are that simple. No, not all proofs are that short. No, not all proofs require so little math. A lot of proofs require a lot more math, or a lot longer, and a lot more complex, but it doesn't make them any more beautiful or any less creative for that matter. And the thing I find amazing about Cantor's diagonal argument, which is what it's called if you want to look it up later, is that he couldn't have learned this in the classroom. This isn't about algorithms. This isn't about multiplication or anything like that. This is a truly creative answer. It's a truly creative answer to a problem. And we need to start showing students in high school, earlier than that, this is what math is and this is what math can be. Math can be as thrilling as a movie, as deliberate as a book, inspiring as a poem, and as important as any scientific discovery. I'm not saying we should ditch the math curriculum. That wouldn't work. But because most of the computational skills taught in math classes are kind of crucial to a lot of these proofs. But purely computational information needs to be supplemented with creative material. And a lot of people say, okay, well this is impossible, especially for younger kids. They can't understand stuff like that. Yet evidence says otherwise. A recent study published in The Atlantic found that 5-year-olds are capable of conceptualizing calculus. And I've seen this firsthand. I help run a middle school club for math girls at Lincoln Elementary called Mathematicals. It's like a pun, like mathematical. And we've gotten these young girls to like understand these super